Hello everyone. Today I would like to present you my work on the identification of the dispersion curves and the damping loss factor using hybrid inhomogeneous wave correlations Green's function method. The context here is to predict the vibratory and acoustics level in the interior and the exterior of the vehicles. The first objective is to implement and to validate the inhomogeneous wave correlation methods and to overcome limitations of some other methods. First, the dispersion relation in function of the heading angles for each frequency using IWC method is defined by maximizing the correlation function below. A harmonic measured or calculated spatial field is used as the primary input, correlated to a well-defined inhomogeneous waves in a wave number space domain. The dispersion relation is then interpolated and tabulated in function of the angles and coordinates. Knowing the dispersion relation for each angle, we can now introduce the Green's function. The objective of introducing this new function is to consider the wave propagation from the excitation point. The information on the imaginary part of wave number allows us to estimate the damping loss factor. An aluminum panel with a thickness of 4 mm is tested. The structural damping loss factor is defined at 5% and 10%. First, the dispersion relation is estimated. Here are two examples of the dispersion cartography at 1600 Hz and 5100 Hz. For the dispersion curves and the estimation of the damping loss factor, both correlate well between the proposed methods and the theory. We can now move to the experimental validation. The setup of the experimental study is shown as follows. The test was done over a 1 meter and 1.5 meter sandwich carbon fiber honeycomb panel. The definition of the panel is shown below. Applying the IWC methods, we can thus determine the dispersion relation in function of the angle. The dispersion curves at 0 degree and 90 degree are observed and compared to analytical general laminate model. Both correlate well with the analytical solutions. For the damping loss factor, the half power bandwidth method, the power input method, the decay rate method, and the all IWC methods are compared to the proposed method. The proposed methods correctly estimate the damping loss factor from 3500 Hz. In low frequency range, the method is limited due to the reflection of the boundary. This method allows us to predict the dispersion curve precisely. For the damping loss factor, the estimation in high frequency range correlate well with other methods. The perspective is to improve the estimation of the damping loss factor in low frequency range and to characterize more complex structures.